Okay, so this is part two to the atomic theory lesson 1.4. The next scientist I want you to know is his name is Rutherford, Ernest Rutherford. He's famous for his gold foil experiment, which is a pretty neat experiment that told us a lot about the overall structure about the atom. So what he did is that he used alpha particles, which are positively charged, and he took them and he shot them straight through a gold foil. And this gold foil has a bunch of gold atoms. And um and based on what we learned, according to the law of multiple proportions, these atoms have the same mass. According to Dalton's theory, these atoms are identical, assuming they're not isotopes. They are all identical. Um, And basically, that was just a little review. But what he did was he shot alpha particles straight through, and 98% of the time, the alpha particles went straight through. 98% of the time, the alpha particles went straight through. And then, in rare exceptions, did they bounce back? Okay. So, if most of the alpha particles went straight through the gold atoms, the atoms that are found in this gold sheet, what does that tell you about the structure of the atom? If you were Rutherford and you existed back in the days, I don't even know when, probably in the 1800s, um, you you shot these alpha particles straight through, and they went and very few of them bounce back. What does that tell you about the structure of the gold atoms or the atom in general? What does that tell you? So go ahead and pause it and think about that. Um, Go ahead and think about that. Here's another visual. Most of the atoms went straight through. I mean, most of the alpha particles went straight through the atom. What does that tell you about the structure of the atom? If you were a scientist, what would you propose? Okay, go ahead and pause, and when you're ready, go ahead and unpause and press play. Okay, so now that you had time to think about it, you could have came up with two things. From the experiment, you could infer or propose that because most of the alpha particles went straight through, the atom is mostly empty. It's mostly empty space. And two, because some of the alpha particles shot back, reflected, that means that it does contain something, but it's really, really tiny. It's really, really dense, and it's positively charged. And it's since it repelled, right? It repelled the positively charged alpha particles. They didn't attract. They didn't stay. They didn't stick onto the gold foil. They repelled. So it's positively charged, and that positively charged region was later called the nucleus of the atom. Okay, I'm not talking about the nucleus of a cell. We're now talking about another nucleus, which is the nucleus of an atom. Which this atom, now we know it's not, it's not like plum pudding where they're evenly distributed. All these particles are evenly distributed. No, it's actually mostly empty space. Let's go back to this outline here. So we know that Democritus came up with this idea that atoms are tiny particles; they cannot be divided. So that's that. And then J.J. Thomas said, "Oh, you know what? Because of the cathode ray tube, you shot these cathode rays and they attracted these charged plates. They have charges, and I think they're evenly distributed along this atom, just like water is evenly distributed in the sea, or just like raisins in the pudding, they're evenly distributed when you make it. Um, and what this J.J. Thompson I'm sorry, not J.J. Thompson. What Ernest Rutherford disproved was a plum pudding model. So it showed that this model was not right. It showed that the atom is mostly empty, and it's um, the atom has a positively charged region called the nucleus. So that's when the Bohr model introduced. So here's the Bohr model. It shows an atom um, as a small positively charged nucleus surrounded by electrons that travel in circular orbits around the nucleus. This is similar to the structure of the solar system, but with attraction provided by electrostatic forces rather than gravity. So, I basically just read the slide for you, but let me move this. So this is the atom. There's a positively charged nucleus, and the positive charges on the inside of the nucleus and the protons are attracted to the negative charges on the outside of the electrons. Okay, so this is called an electrostatic attraction, which was later proven to be false because if this model were true, what scientists and physicists said was that the negatively charged electron would eventually collapse into the nucleus if there was a lot of electrostatic attraction. Why doesn't the electron collapse in this model? Um, and if they're orbiting, they're supposed to lose energy as they're orbiting, so the electron is supposed to crash into the positively charged region. Because in physics, when you move, you release energy, and the electron is supposed to be, um, I guess you could say, it's supposed to um, inject itself into the positively charged region because opposites attract, right? We learned that from Rutherford's experiment. Now, this model was also proven to be incorrect. However, it is very useful in chemistry. So we're going to use the model for now, the Bohr model for now, because it's useful when talking about bonding, and it's useful when talking about the number of subatomic particles. So subatomic particles are electrons, neutrons, protons. The correct model that we use today, we went from the Bohr model, which you probably learned in middle school. And sadly, it's not the true model, so I don't know why, it's heavily emphasized by, middle school teachers or high school teachers, even high school teachers. But the true model of the atom is called the quantum model, which you probably have never heard of because it is very complicated. So the quantum model is the most important model. It is the correct model based on the data that we have now. So let me just read the PowerPoint to you and I'll elaborate. It says, but then scientists found that the electron behaves like a wave, meaning that electrons actually spread out and they don't orbit the nucleus like planets orbit the sun. Instead, the atom is described with orbitals. So orbitals, not orbits. We don't use the word orbits ever do I want you to use the word orbits. Instead, these electrons move around something called orbitals, which are regions of space with a probability of where an electron is found. So what does that even mean? So um, what it means is this. This is called an s orbital. This is a region, an area, okay? It is an area, it is a probability of where the electron is going to be found because the electron does not move in a circular way. It moves randomly and it spreads everywhere in a specific region because of a specific amount of energy that it has. So we say that it's in a specific region. Um, so this is called an s orbital. And then once you have something with a lobe like this, like a dumbbell, then it's called p. And when you have two dumbbells, then it's called d orbitals. Okay, so the shapes, there's different shapes. So you should know that the atom has a bunch of these orbitals, and in these orbitals there are electrons, and you don't know exactly where the electron is because it's a probability because they keep moving and it's a probability of where you're going to find them. Okay, so the last experiment is the Millikan oil drop experiment. this experiment, I don't really want you to know it. Um, but basically, Millikan, what he did is, um, he um, he basically levitated a few drops of oil, and based on the amount of radiation, he was able to find the numerical charge of the electron. So what I want you to know about this is that charge the charge is measured in units called coulombs. Okay, coulombs. So again, negative, positive charges are measured in units of coulombs. For example, one electron has a charge of negative 1.6 times 10 to the negative 19 coulombs. Okay, that's um, abbreviated with a C. Okay, so that's what I want you to know from Millikan's oil drop, just that he measured the amount of coulombs in in an electron. Okay, um, and going back to this experiment of radiation, and Madame and Pierre Curie are famous because, first of all, Madame Curie died from radiation. She basically poisoned herself, and she is one of the most um, known female scientists to ever exist because she was the one that discovered uranium, and she discovered that uranium was radioactive, and radioactivity meant that the atoms were unstable, where they released a bunch of energy in the form of radiation. So based on this, we already talked about this. Based on this illustration that you see here, we can see that radiation was shot through, and um, some of it repelled the positive charge. So the alpha rays repelled the positive charge plate, meaning that the alpha particles are positively charged. Gamma rays have no charge, and beta rays are negatively charged since they attracted a positive plate and reflected the negative plate. So alpha particle is helium. So helium is actually what's spit out from a radioactive atom when unstable, and alpha, based on this diagram, you could conclude that alpha particles are positive. So here you would put that they are positive. Okay, and then beta is negative, and gamma is neutral. Okay, so gamma is neutral. Um, so that will conclude our part two. There's one more part. I apologize. I know it's a lot, but there's one more part. Take a break, take a day off. The next day, come back and tackle it. The next part is basic chemistry. You probably learned it in middle school, but I really need you to know it. You need to know it by heart, okay? I don't need you to, oh, I kind of know it. I need to know. You need to know it, okay? So, go ahead and proceed to part three if you feel like you're ready for it.